Hello everyone, thank you for joining me today for this Creating a Safe Electrical Test Area webinar. We're going to be taking a common sense approach to this today and go over all the things you need to take into consideration when setting up a safe working area. We're going to cover these 5 steps here. We're going to look at the understanding the effects of electric shock, protecting against that electric shock, the types of test station you can use to keep your operators safe, operator training and skills that the guys on the line are going to need to actually keep themselves and others safe, and then test equipment considerations to finish off with. So who are Seaward? We're a world-leading electrical test equipment manufacturer. Been around since 1982. We've proudly manufactured premium electrical safety test equipment for customers across the world who share our appreciation of quality and want to keep more people safe. We offer 450 electrical safety solutions, so kind of a huge range of solutions. We support 7 OEM partners across the world, bringing their visions to the market. We've got a team of over 167 people, proud and engaged. We have experts with over 38 years of keeping people safe and working with 60 distribution partners worldwide to get our products to kind of every corner of the world. And we operate from 2 locations in the UK and the United States. So the first thing I want to talk about is understanding electric shock. The severity of an electric shock depends on several factors. The first one being the amount of voltage and current. So both of them are important in terms of how severe an electric shock will be. The second one is going to be condition of the body, how the situation that your body's in at the time, if it's damp, if you're sweaty, anything like that, it could create an ideal situation for a shock. The path the shock takes through the body, or the current takes through your body, is really important to determine how bad the kind of results of the shock will be, and the duration of the exposure is also important. We're going to talk about kind of how to mitigate all of these risks in the different stages of this webinar. So there's a kind of perception of electric shock where this little chap here is kind of demonstrating it. You shake around a little bit, your hair stands on end, and that's kind of partly true. You do get involuntary muscle movement during an electric shock, but this could be more serious than just shaking around a little bit. It could mean that you could fall off something if you're climbing a ladder or something like that. If you get an involuntary muscle movement, it could cause you to fall. If you're dealing with something sharp or something dangerous, it could cause you to cause injury to yourself or someone else. And of course, it might mean that you're unable to let go of whatever it is that's giving you that electric shock. And an electric shock can cause burns, and it can also cause issues with your heart, which is controlled by electrical signals, which can be fatal too. So the reality of current exposure, the amount of current is really what's going to cause the damage to you. So we're going to talk about mains voltage here, so about 230 volts at 50 hertz AC, that's UK mains voltage. And on the right there you can see kind of a list of different current levels, and on the left is the physiological effect of those current levels on the body. So at about 0.5 milliamps, it's generally not perceptible. You wouldn't be able to tell that you're getting a shock at 0.5 milliamps. What you were touching would possibly feel a little greasy, but it wouldn't feel like you're getting an electric shock. About 1 milliamp is the threshold of perception, where you get a kind of tingly sensation. You might have felt this before if you were getting a mild shock from something. Higher than that, at 5 milliamps, is what we call the maximum let go current. Below 5 milliamps, you're able to comfortably let go of something, whereas above that, at around 10 to 20 milliamps, is a painful, can't let go. That means the current is kind of overriding the signals that your brain is sending to your muscles, causing them to contract, and you can't let go, and it is painful. So around this area, we're starting to get into dangerous territory. Around 30 milliamps, a current can cause severe pain, muscular contraction, and difficulty breathing. So this is where you're going to need help to get yourself out of a situation. If you've got hold of something that's giving you an electric shock at this point, you're not going to be able to release it. It can cause severe pain, and obviously the difficulty breathing, your muscles in your chest that control breathing, your diaphragm and intercostal muscles, are all controlled by electrical signals, and if those signals are interfered with, that's going to create obviously difficulty for you to actually inhale. Possible ventricular fibrillation after 3 seconds at 0 0.1 amps, and death is possible. So if you receive a shock of more than 0 0.1 amps for more than 3 seconds, it can actually interfere with your heart. Your heart, of course, is a muscle, again, controlled by electrical signals, and a current of 0 0.1 amps is enough to mess with that signal enough to possibly cause death. From about 1.5 amps, skeletal muscle damage is highly likely, and death will probably follow. I just want to point out a couple of these current levels. So for 5 milliamps, there's probably those of you out there who have recognized this from either production line testing or higher industry testing. This is the limit that's applied by most of the guidance in those areas. I also want to point out the 30 milliamp, that's the common maximum current allowed by the majority of domestic RCD devices. And they're designed to interrupt the supply within a few hundredths of a second to reduce the exposure time if the worst was to happen. So if someone was to get a shock, they're designed to cut that current almost immediately. So understanding the current condition of the body is important. The average human has a resistance of approximately 1 to 2 kiloohms. Your skin provides much of that resistance. Internal flow is much easier, as again your nervous system is designed to carry currents around your body. Once a current gets inside your skin, it's very easy for it to travel around inside. So an example of when the condition of the body is really, really important is if someone was undergoing surgery. So we've talked about the skin being the barrier to most of the current, and your kind of highest resistance. And once that current is past your skin, then you're in real danger. And so if someone's in an operating theatre and a surgeon is working on the internals of a person, they've already breached that skin barrier. So smaller currents pose much more of a risk when the skin isn't there to stop it. So things like surgical equipment are allowed a much lower leakage than non-surgical equipment. But that's a good example of kind of how the skin is an important insulator for us. The path of the current is really, really important. Shock occurs when current flows into and out of the body. A lot of what we're going to talk about today is kind of isolating you, making sure that if you did come in contact with something that was, say, live, then the current couldn't flow into you and out of you. Current flowing across the chest poses the highest risk because that's where your heart is. And the current path could exist where two hands are in contact with poorly insulated product and flowing to earth. So that could be that your left hand is touching the equipment that you're testing and your right hand is touching something else that's grounded. So it might not be that it has to go through your feet, that your feet are grounded. It could be that it goes into you one arm and out of the other arm, and that would cause a shock. So how are we going to protect against electric shock? We're going to reduce the potential for current flow through the body. We're going to do that by putting insulation in between you and it and making sure that you're isolated from ground. We're also going to reduce the duration of the exposure, so we're going to use things like safety shutoffs and RCDs to cut off the power if there's any leakage detected. And we're also going to reduce the risk of occurrence of a shock by training and letting people know kind of what the risks are and how to mitigate those risks. So when do we apply the standards? So mainly we're going to be talking about EN 50191, that's for the UK and Europe. Voltages at frequencies above 500 Hz and exceeding 25 volts AC or 60 volts DC, and do not comply with the requirements for SELV or PELV. We also apply the standard at voltages at frequencies up to 500 Hz exceeding 25 volts AC or 60 volts DC if the resulting current through a non-inductive resistance of 2 kiloohms exceeds 3 milliamps AC or 12 milliamps DC. So you can see that the limits that we're talking about, kind of 5 milliamps and that kind of thing, is higher than that, so we need to apply this standard. Or if the discharge of energy exceeds 350 millijoules. And then for the USA only, they need to take into account the standard, the OSHA 29 CFR Part 1910.332 Subpart S. When exposed voltages are in excess of 50 volts, operators should be trained and qualified to perform electrical testing. The first thing we're going to talk about in creating a safe working environment is we're going to look at how to protect the operator. So we're going to use insulated test areas and safety disconnection of supply to both lower the chance of a shock and to make sure that if a shock occurs that it is time limited and it won't happen for very long. The next thing we'll look at is prohibitions and safe zones and warning and information signs, which are all there they are designed to help non-trained personnel be aware of the risks and not kind of be in a situation where they could get a shock. So we'll start with the test area workstation and the recommendations that the standards make for those. They recommend that it's fully insulated, so ideally you want something made of wood, rubber, or plastic, such as that image in the photo there. If you have to use a metal framed bench, so it might be wooden topped with a metal frame, make sure that it has an insulated top. So if you are using a metal bench, have wood on top, have rubber on top, something like that, something insulated. And no conductive fixings should be visible on the top. So you don't want that wood being screwed down with bolts into a metal table and those bolts be visible on the top, because they are, of course, providing a path to ground into the metal chassis or the metal frame and then down to ground. At the time of test, we only want one item to be on the bench at any time. The theory being that if you have a bench full of things you are testing or about to test, if one of them becomes live, it could then cause a chain reaction where something it's touching becomes live, the next thing becomes live, the next thing becomes live, potentially leading to a situation where something is live that you wouldn't expect it to be. The test bench should also not extend outside the test area for the same reason. If you have a very long test bench and the bench is, say, metal framed or anything like that, and the bench somehow became live, then we don't want someone outside the test area using that same bench or being able to touch that bench, and they could receive a shock if the bench had become live. Insulated rubber matting is really, really useful for both something to stand on and for bench topping. It provides a barrier between the live parts and ground, so we're isolating those parts from ground. It should be installed over any metal, concrete or ceramic flooring. It's really, really important not to test on those kinds of floorings. They're all very good conductors, really good at taking a charge from you or your equipment down to ground, and that's where the potential for shock lies. Also use it to cover the worktops where required. And it should be suitably rated for the voltage that you're using in accordance with IEC 61111. So in the terms of the kind of tester that we'll talk about today possibly is a unit we call our HAL, and it has a max output of about 6,000 volts, and so we would need a class 1 mat for that, because even if we were testing at, say, 1,000 volts AC, we need to think in kind of worst case scenarios. So if the tester can output 6 kV, that's the protection that we are looking for. So rather than go for a class 0, we're going to go for a class 1. You should cover the whole working area, but the working area should be no smaller than 600 millimeters by 600 millimeters, about 60 centimeters by 60 centimeters. This matting usually comes in kind of rolls, as that picture there, about 1 meter by, say, 10 meters. So usually the working areas end up being around 1 meter by 2 meter, giving the operator enough space to move around. Test area exclusion zones. These prevent access to the test area by persons other than the authorized test personnel. They also prevent persons outside the barrier reaching the operating devices, the test equipment, or inside anything located inside the barrier. So that's really important. So we want to try and keep untrained people out using these barriers, but we also want to make sure they can't reach in and touch anything from outside those barriers. So the distance between the barrier and the prohibition zone, it will change depending on the height of the barrier. So if you have a 3-foot barrier, it needs to be a little further away from the prohibition zone to stop people reaching over it. If you have a 5 or 6 foot barrier, it can be a lot closer because they can't reach over and touch the operator or the equipment or the device under test. We need to ensure really good visibility into the test area, ensuring the test operative can be seen at all times. So you might be tempted to build a big wooden box and entirely enclose your test area. It's not advised. The recommendations are very clear that you ensure good visibility in the test area. All kinds of standards have this, that you shouldn't work alone anyway, but we don't want a situation where the operator gets into some difficulty and no one can see him. So ensure good visibility into the test area at all times. Test area signals or beacons. The colour doesn't indicate the test status here. It doesn't say pass or fail. It says kind of green if it's ready to operate, so it's turned on. it's ready to go. But a red signal means danger, so it's ready to test. So it's either one button away from going, or it is testing at the time. These things are really useful for non-trained personnel because obviously they see a green light. Green normally means everything's okay, and a red light means danger or stop. So it's a good, really basic indicator to get untrained people to not approach a test area. The test area electrical supply, there should be a manual switching element or an emergency stop, and it should be red with an orange background, like the ones in the picture there. And there should be an automatic switching element as well. It should be fitted with an RCD protection. So it's the likelihood is that the electrical system that you're using, it does have an RCD. The way an RCD works is it measures the current going down the live, and it measures the current coming back, the neutral, and if it decides that some of that current has gone astray somewhere, possibly going into somebody and down to ground, then it will cut the power immediately. Our testers will also cut off after they go above the current that you define. So something like 5 milliamps, if you go above the 5 milliamps, it would cut off. But again, you define that cut off level. Test area installation signs are really, really useful. Things that say danger, electrical test area, high voltages, electrical shock risk, do not enter when red light is on, authorized personnel only in this area. Really good at keeping out non-trained personnel and advising them that the equipment is dangerous. It might not look particularly dangerous, but it is, so we need to make sure that people are aware of the danger. We get asked a lot about electrostatic discharge protection areas. Do not use a tester in an ESD area. ESD areas are designed to protect components from static discharge by providing a path to earth. That is the opposite of what we're after here. So it totally contradicts our aim, which is isolation. So we are trying to prevent any current going from you or your equipment down to earth. ESD areas, they provide a path to ground and could create a shock hazard if the operator is exposed to the test voltages. So do not test in ESD areas, and also while wearing ESD devices. So they could be the robes, the foot straps, the little wrist bracelets that you plug into a socket or clip to a radiator, those kind of things. We don't want any of that. We want to keep you isolated. If you do work in an area that has ESD protection, you will need to create an isolated test area separate from that ESD protection where testing will take place. And by all means follow the ESD procedures up until the edge of that test area to keep the equipment safe. But once that equipment is being tested and in the test area, our main concern is keeping the operators safe. So we're going to talk about mainly two of the four different ways of setting up a test station. So the two we're going to talk about are a test station without automatic protection against direct contact and a test station with automatic protection against direct contact. You also get temporary test stations which need to apply all of the same factors that we're talking about today, so exclusion zones, warning signs, things like that. The difference is that they can move around, so you might have a trolley with all your equipment on it, you set up a test station. Say if you were testing a larger piece of equipment, it wouldn't make sense to bring that equipment to the test area, take the test area to the equipment, but apply all of this knowledge in the same way. Laboratory or experimental test stations also kind of vary a little bit more, but again, you need to apply all the same theory to them. But we're going to focus first on a test station without automatic protection against electric shock. So without automatic protection, that basically means that during a test, the operator could come in contact with the equipment that they're testing. Extra consideration must be taken into account to ensure that the area is isolated. So connections might be made by the operator using probes, so they might be using a probe in one hand. It's important to train the operator to know what the dangers are, because if they did something like held the equipment with their left hand and used the probe with their right hand, there's a danger of a shock there. So there's a training consideration to be made if there's not automatic protection. But again, I can't emphasize this enough, testing should never be made in an enclosed room with no visibility of the test operator. Okay, so never in a kind of enclosed room, guys. So this is what a gold standard, if you like, test station without automatic protection looks like. So this is a kind of production line. Now, if I just jump back a few slides here, it might be that this kind of setup is better for you. Again, we're just applying the same things to a lot of different situations. So this could be gold standard for you. It's got the exclusion zone around there, the beacons, the signs, the stop switches, but it's obviously a lot more compact. It's probably built more for batch operations than a kind of production line like this one is. But this production line is a kind of a gold standard for this. And you can see everything there. You can see the emergency stop switches clearly marked inside and outside, signal lights. The test bench does not extend outside the test area. So in this case, the gentleman there is using a conveyor belt. It would be much easier to have one conveyor belt running through the whole thing there, but you cannot do that. You need to have a test bench separate inside. Again, the theory being, if that conveyor belt went live, that colleague in dispatch could get a nasty shock from the end of that conveyor belt if the whole thing was joined together. The equipment is isolated, so you can see that washing machine or tumble dryer there is on a wooden pallet on top of the test bench or test conveyor. The working area is movement's not impeded. He's got plenty of space there. He's also standing on rubber matting, and he is himself a skilled and instructed person. The test equipment is connected to a method of automatic disconnection of supply, so an LCD or something like that. And the benches are constructed from insulating materials, so that conveyor could be a plastic conveyor, something like that. And clear warning signs are there to identify the test area and warn other non-trained personnel not to enter. For a test station with automatic protection, the theory here is that the equipment is tested inside an enclosure, so something made out of plastic or wood or something that is isolated. So opening the enclosure will disconnect the voltage. Opening the enclosure stops the testing, which means contact with the equipment under test can't occur during the test. Barriers may be omitted in this case when there's automatic protection, because it doesn't matter how close you get to that box, you can't touch the equipment while it's being tested. But again, testing should never be made in an enclosed room with no visibility of the test operator. So this is what that looks like. You can see it's a lot cleaner, a lot simpler. Yes, again, it's not ideal for everyone. I mean, this guy, if he's only making that one piece of equipment, he could have a test box there at point A that is the right size. If you were making all kinds of things at different sizes, or if you were working in the higher industry where you were testing everything that was coming back before hiring it out again, it's difficult to have an enclosure that fits everything. But again, we're just applying the same knowledge to the situation that we ourselves are in. But you can see at point A there, there's actually a transparent case on top of that. So there is a lid, and opening that lid will disconnect the test voltage. So at B there, that's a little image of our HAL. It will disconnect the power if that enclosure is opened using the guard switch. There are plenty of ways to do that. You could use your own interlock system, but all of our testers do have a guard switch system that you can implement into that. Barriers may be omitted in the test area with automatic protection, so if it's got an enclosure, you don't need the barriers. But you still need to have a skilled and instructed person, and the benches still need to be constructed from insulated materials. So operator training, we need to cover kind of four areas. How to prepare for working, so kind of PPE, what they need to do to make sure that they're in a safe environment. We then need to talk about how the test equipment functions, so how to actually perform a test with the equipment, when it's dangerous, when it's safe, exactly how to use that equipment, the information the equipment gives the operator, that kind of thing. They need to know how to inspect test leads and fixtures, so they need to know how to make sure that for one instance that their area is safe, but also how to visually check the equipment that they're testing. Both are really, really important. And how to verify the test equipment, how to verify it on a regular basis to make sure it's working and make sure it's actually correctly identifying fault conditions. So I'll go over all of these in detail. So in terms of preparation for working, we need to consider what PPE should be worn. So is it insulated boots? Is it insulated gloves? We need to think about how we operate the emergency stop features in the event of an incident. So the operator needs to know that switch is there and how to use it, and other people around should know how to use the emergency stop outside the area if the operator is in trouble. We need everyone to know that only trained staff should be permitted to enter the test area unless accompanied by a supervisor. And where to find and interpret the instructions for use of the test area. The instructions should always be available for operators. So if the operators have any queries or forget how to do anything, the test instructions or standard operating procedures, whatever your organization calls them, should be there and should be available for the operators to find, and they should be easy to interpret as well. So the test equipment functions. The operator will need to know what tests are being performed and the risks involved. So the different tests have different kind of elements of risk in them. They need to know how to perform the testing safely using the test instruments. So there will be ways in some tests to do it in an unsafe manner. And this is why we have this training consideration, to make sure that they're using it safely. The test equipment will display the test results in different ways. So there are loads and loads of different testers out there on the market. They'll all communicate with the operator differently. It's important that they know how it's displayed and what other information it's giving the operator. So a lot of our testers will kind of give a pass or a fail result, but it might be that the tester your operator is using just gives a kind of a value back, and the operator has to evaluate and decide if it's a pass or a fail. So really important training consideration there. And that during high voltage testing, the unit on the test must not be touched. This is again a really big thing. It's really important. Do not touch the equipment under testing at all. Okay, even if you're isolated, even if you're wearing gloves, doesn't matter. Do not touch the equipment under test. If test probes are to be used, the operator should be trained to understand the function of the probe and how to use it safely. Again, using probes is really high on the list of things that should be considered for training, because they are near the equipment, they are near the danger, and it's important to know how to kind of get through those tests safely. So inspecting test leads and fixtures, so in your safe working area, we need to make sure that any fixed connections are properly terminated. We don't want them to be loose or making poor contact. They could either present a safety risk or an incorrect test connection. So either of those are really bad. We don't want to present a risk to our operator, but we also don't want to be incorrectly testing products. We need to make sure that all leads are in a good condition, and we don't want any exposed internal conductors. If there's any exposed internal conductors in anything you're using to test or anything that you're testing, do not test it. Do not continue with the test. That needs to be dealt with first, which is why tests have things like visual tests. This is very similar to a visual test if you're actually testing equipment. We want no signs of damage or due to misuse or anything else, really. We want to use really good condition equipment. If there's any damage to it, it could have damaged the insulation and could potentially cause an electric shock. That any fixtures used are not damaged and any connections to those fixtures are sound. So check your equipment, check your whole area for any damage or anything that could cause a shock. Really important. Inspection of test leads and all the fixtures. Verifying the test equipment is really important too. It's normally done with using a known resistor value designed to create a fail condition. The theory is that if you are using a tester, you want to make sure that that tester can correctly identify a fail condition. The way we do that is by using something like that Y160 on screen there. The idea is that the tester will trip if the currents are working correctly and the instrument is not allowing items to go out incorrectly tested. So what will happen is you'll run a test. This thing will be designed to fail that test. The tester will say fail. It'll cut the power. That's great. That's verified that the tester is correctly identifying a fail condition. And these fault simulators are a really simple way of performing these checks, and you can keep a record of these checks. We recommend doing this daily, but it might be that you do it twice daily, or it's entirely up to you. So if you want any more information on EN 50191 and how to set up a safe working area, head over to our website at seaward.com and search for 50191, and you'll find our free guide, really detailed, really useful guide there, and also a handy safe working area infographic. It could be something you just print out and put next to your working area, but these are great if you want to set up a working area or if you want to just kind of audit the one you've got.